Here are solutions to homework set number 6 for ECE 376 Embedded Systems. This homework set looks at data collection and statistics, specifically chi-squared test. Now the first problem is to collect data. I want to measure temperature with my PIC processor and record a bunch of data points. So here's what that looks like. I am currently recording the raw analog voltage. This is the A to D count is 549. This is the voltage on port A pin 1, 2.67 volts. This is the implied resistance. I've got a voltage divider. Here's my resistor. There's the thermistor. This is 1158 ohms. And the implied temperature is 21.79 degrees Celsius. Now using the super amazing flash tool, I'm recording voltage, resistance, and temperature. Take that data, throw it into MATLAB, we'll copy it. So clear the data, collect a bunch of data to clipboard, put it into MATLAB, and I can start analyzing it. The code itself is actually fairly short. The main loop is just read the analog input, convert to voltage, convert to resistance, convert to Celsius, then display everything on the LCD display, and ship everything out to the serial port. Repeat every 100 milliseconds. The resulting code is 7,790 bytes. Divide by 2, that's how many lines of assembly it is. So it's actually a fairly involved program. In C, it's not too bad. In assembly, that'd be painful. Once I get the data, I've got 3 columns of data. I can throw that in MATLAB, pull off the last column, and with that, I can find the mean, standard deviation, sample size. So this is the average of the temperature. Here's the standard deviation. There's the number of data points. And if I plot it, here's what the data looks like. What I'm looking at are quantization levels. So the A to D converter is an integer, 0 to 1023. Each one of these is one count, 1 bit. So that's kind of what the data looks like. To get it smoother than that, it's just going to be noisy. If I had a high resolution A to D, like a 12-bit, 14-bit, it'd be smaller. If I had an op-amp circuit, rather than just take a voltage divider and read it, if I had an op-amp, I could amplify the voltage, spread it out some. I didn't do that. I just took a voltage divider. Keeps it easy. Once you get the data, I now want to do some testing. A chi-square test is the test of a distribution. Let's test to see, does the data follow a uniform distribution? So the smallest voltage is 21.36. The largest is 21.62. And with the quantization levels, there's actually only 2 other points in the middle. A uniform distribution would say each of these has the same probability, each has the same frequency. Let's see if this really is a uniform distribution. Well, what I do with a chi-square test is I first split up the data into bins. The expected frequency is the number of data points times the probability of landing in each bin. For uniform distribution, each one's 1 in 4. Here's the actual data. Calculate the difference squared, divide by 57, difference squared, divided by 57, add them all up, I get 164. And it's pretty darn obvious this is not a uniform distribution. Chi-square test doesn't tell me what the distribution is, but it does tell me whatever it is, it ain't that. Next problem. Let's look at the following code. This code generates a random number between 1 and 7. What happens is when I hold the button down, RB1, actually I'm using RB1 because my RB0 is broken, it just counts really, really fast. When I release, whatever the count is, that's my random number. So kind of like here, I press, release, I roll to 4. Press, release, 6, 5, 3, 7. Now using the data logger, I can record that data. So over here, these are my random numbers. I can collect a bunch of data. Once I have the data, I want to find out, is this really a fair die? Now it's not really clear if this is or isn't. When I count mod 7, I could count 0, 1, 2, 3, 4, 5, 6. 6 plus 1 is 7. If it's 7, go back to 0. That extra coding to go back to 0 on 6 means that one number appears. I spend extra time on that one number. There's a higher probability that when I release the button, I'm going to release on that value. Does that show up in the data? That's a chi-squared test. To do a chi-squared test, I first collect some data. So I roll the dice a bunch of times. Here's how many times I got each number. I then calculate the chi-squared score. If this is a fair die, all numbers have equal probability, 1 in 7 chance. Here's the expected number of rolls for each number. Here's what I really got. Calculate the chi-squared value. That's the difference squared divided by 26, difference squared divided by 26. Add them all up, I get 11.8. To convert that to a probability, I use the chi-squared table. The chi-squared table, I would have 6 degrees of freedom. Chi-squared value is 11.87. Convert to a probability, corresponds to 94%. To illustrate that, if we go to StatTrack, one of the all-time great websites, I've got 6 degrees of freedom. My chi-squared value is 11.87. 11.87, compute, and 93%. Or rounding 94%. So 94% certain this is not a fair die. Maybe, of course, the number that shows up too often is right here, is the number 3. I don't know why 3 would be special. I kind of expect to be either at the 7 or the 1. It could also be that this is just random data. Sometimes you get numbers that big, sometimes you get smaller numbers. Not really clear. Okay, let's take another case. If I throw in this line of code, this says 10% of the time I'm always going to roll a 7. The rest of the time the die is fair. Is that a loaded die? Well, if I can see the source code, then yeah, of course it is. If I can't see the source code, can I tell just by rolling the dice and seeing the outcomes? The procedure is same as before. Roll the dice a whole bunch of times. Here I rolled it 218 times. Here's the frequency. Again, I'm getting too many 7s. That's showing up in the data. Convert that to a probability. Again, do the chi-squared table. Now with the 218 rolls, here's how many times I should get each number. Here's how many times I did get each number. Take the difference squared, divide by 31. Difference squared, divided by 31. Add them all up, I get 19. What that means, if I have a chi-squared score of 19.47, 6 degrees of freedom, meaning 7 bins, that's 99%. So at this point I could be 99% certain that this is a loaded die. Of course, that was with a lot of die rolls. What it kind of works out to is you can detect loading if you have enough die rolls. If you just have a couple die rolls, like 50, it's really hard to spot 10% loading. Problem number 5 says, okay, how loaded is too loaded? Well, to answer that question, you have to make some assumptions. Like, let's assume I'll roll the dice 210 times, so I should get 30 7s, 180 numbers that aren't 7. I'm getting x too many 7s, and x too few, all the other numbers. How large can x be and only be 95% certain that the die is loaded? Well, to do that, take the difference squared, divide by 180, difference squared, divided by 30, add them all up. That's the chi-squared value. From StatTrack, I've got 2 bins, meaning 1 degree freedom. And with 1 degree freedom, I want to be 95% certain that the die is loaded. I need a chi-squared value of 3.84. So this number is 3.84. I have right on the edge of detecting it. And that works out to x is 9.9, basically 10. So we're going to have 10 too many 7s, which is 10 and 2 to 10. I can have about 4.7% loading and get away with it with a probability of 95%. That's one thing you can do with a chi-squared test. I can calculate how loaded I can make a die and get away with it. And again, this kind of makes some assumptions. If I roll the dice more than 210 times, I need less loading. If I roll it fewer times, like only 50 rolls, I can load it more heavily. That's chi-squared test. The last problem is to find out if I'm psychic. So here what I did is I flipped a coin 10 times, predicted whether it's going to be heads or tails, and I was right 6 times out of 10. Does that mean I'm psychic? Well, that too is a chi-squared test. I expect to be right half the time. I was really right 6 times. Is that significant? We'll take the difference squared, divide by 5, difference squared, divide by 5, I get 0.4. Go to stat track, I've got 1 degree of freedom. My chi-squared value is 0.4. That means 47% chance I wasn't just guessing. That's basically 50-50. That's basically no conclusion. So sadly, I'm not psychic. But that's homework set number 6 for 376, data collection and chi-squared test.